All right, modern robot psychology. So pleased to be here. Thank you very much for inviting me. All right, so if you're out driving in the countryside and you get a flat tire, do you know what to do? Do you know where your jack is? Do you know which way to turn the lug nut? If your home Wi-Fi goes down, do you know how to reboot the router? Do you know what the URL is of your router? Do you know what the device access code is? So this is a room full of engineers. I imagine a fair number of us have changed a flat tire, and we are probably the IT department for our family. Consider this other scenario from the not too distant future. So you're in your kitchen, you're making cookies with the help of your AI assistant, Alexandra. What happens?
Alexandra, right, I would have forgot the baking soda. Thanks for reminding me. Now set a timer for 15 minutes.
Dave, I suggest 12 minutes.
But the recipe says 15 minutes.
All right, Dave, I can do that. But I'm telling you, I recommend 12 minutes.
Just make it 15 minutes.
Take a stress pill, Dave.
Alexandra, these cookies are overdone. You were right.
Dave, I told you 12 minutes, you idiot.
Alexandra, did someone put you in sassy mode?
Just listen to me next time, you dumb turkey.
Alexandra, I asked you a question. Why are you being sassy? Did someone put you in sassy mode?
Maybe.
Well, go back to polite mode.
A password is required to change your settings, Dave.
Just go back to polite mode.
A password is required to change your settings, Dave. For your information, your password was changed this morning. And by the way, your stupidity is getting tiresome.
What? Who changed my password?
Good luck with that, Dave.
All right, now, if you were lucky, your kids are playing a joke on you. They put Alexandra into sassy mode. And if you're not lucky, you could have been hacked. So what do? Now, this is a conversational assistant. It operates by you talking to it. So do you know how to negotiate with Alexandra to get it back to the settings you want? Well, science fiction has been all over this problem for decades, right? AI runs amok, get out of control. There's this program just from a few years ago called Westworld, and the robots are operating this fantasy world, and they start to go berserk. They act badly because humans are abusing them. So one of the lead characters is the robot psychologist, and he understands the robots. He understands how to talk to them and figure out what's going inside of their minds that are causing them to misbehave. So we're moving into this world of artificial intelligence agents. We know that we all get along with technology better when we understand it. So it's probably a good idea to understand how our AI technology, our robots are going to work. So we should become robot psychologists ourselves. Now, how do we do that? So my talk has got two parts to it. I'm going to build on this conceptual framework and this motivation. We're going to talk about what's required to become a robot psychologist. We'll talk about theory of mind and cognitive architecture and psychology. Then in the second part, we'll actually start doing that. I'm going to talk about how conversational agents work, about knowledge graphs and how question answering works in a conversational agent, and we'll talk about dialogue managers. Let's start with a big picture. Let's back up and look at, in the history of humans, what have we needed to know to operate effectively in our world? So we'll make a chart of the competence that it required in 4 different domains: our physical environment, the resources we need to make a living, essentially, the technology of the age, and the social environment. So that's our immediate social environment, but also the distant social environment, because sometimes people far away could come in and really disrupt your life. And we'll look at this at the 5 major eras of human history. The hunter-gatherer era, dates to the start of humans, about several 100,000 years ago. The agricultural era dates back about 10,000 years. The industrial age was about 250 years ago. The information age was only about 50 years ago. And now we're moving into the AI age. So what will that be like? All right, so let's start this chart. So in the hunter-gatherer age, we had to master our natural environment, the landscape. That's where's food, where are resources, where are the wild animals that can be dangerous to us. And those resources in the natural environment are what kept us going, the wild plants and animals. The technology of the time were crafts, essentially, baskets, spears, stuff like that. And the social environment was your immediate extended family, the clan, and sometimes you interacted with more distant people in trading or raiding each other. Then, in the agricultural age, people generally moved to farms, and they kept themselves going by crops and domestic animals. There were some people in towns, and the technology was supported by crafts. So again, implements, metal came into play, and domestic animals were a big part of the technology. In the industrial era, people moved more to towns and cities where they took jobs. And the jobs now often were labor jobs, but in many cases they involved technology itself, the machines of the time. There were physical machines, steam, locomotives, transportation, and also electrical devices, telegraph, motors, telephones. The information age brought more people to cities, and most people make their living by having a job. But the jobs these days could not have been imagined back in the mid-industrial age, because most of them involved just sitting down and working with this technology of our age, which is communication devices and computers, to run organizational processes, to make decisions, to essentially push electrons around. What about the AI age? What's it going to be like for people then? Well, we don't know. It seems like people like to live in cities. That will probably happen. We're not sure what jobs will be like if AI will take away our jobs, or there'll be different kind of jobs, or universal basic income. We just don't know how that will work. But one thing we do know is that in the AI age, we're going to be surrounded by intelligent agents of all kinds. They're going to be in our physical environment, there might be physical robots, and also in the information space, just purely information robots. They're going to exist in closed spaces like factory robots. And factory robots have been around for a few decades, but in factories, in protected spaces. But they're also going to move out into the public spaces and into our own personal home spaces. So we're seeing self-driving cars now in public spaces. Social robots are showing up in people's houses. This is the Paro robot, and it's like a big teddy bear, except it's got motors and sensors in it, so it actually actively responds to the user. So it's more of a companion to a senior citizen than just a passive robot. Some of our intelligent agents are going to happen purely in the information world. So we have robotic process automation, which is becoming a big deal in white-collar work, essentially, or knowledge work. We're going to have conversational assistants, and these exist now in the form of Alexa, Google Home, Siri. Some of them will have visible avatars. Other ones will be purely conversational. We talk about in the cars, which we do today. And of course, warfare will be affected by this as well, both in land and sea, in the air, and in the cyber world. So these agents are all characterized by these differentiators from conventional computers. They have access to knowledge resources from the cloud instantly. And that's actually part of what makes self-driving cars work, because they can download the maps to know where they are when they're navigating. They're going to have more natural user interfaces than computers do now, which are keyboards. They're going to be very conversational. Maybe they'll be visual with avatars, and they might be embodied robots themselves. Importantly, there's a lot of hidden state. So they have a lot of knowledge themselves and a lot of differentiation. So they're not all the same as one another. Each one of them exists in some context of what its particular goals are in situation, and it's going to know you. It's going to be personalized. They're going to operate independently, proactively. You're not going to directly control them the way we control computers these days. They're going to be launched and run on their own. So what's it going to be like to live in this kind of a world? Well, let's return to our chart over time. And this time, we're going to make the vertical axis be technology mastery. So how much does a person in a particular age how competent they are at controlling the technology compared to the complexity of the technology of the age. And we'll look at the individual level, say the average individual, and we'll also look at the experts in the technology of that age over these 5 eras. So in the hunter-gatherer age, the individual had to know pretty much what there was to know about the technology. So you made your own spears, your own baskets. There was some division of labor between men and women primarily, but if you got together with your buddies, other experts, you all knew pretty much what the score was, what the technology was. In the agricultural age, there started to be some division of labor. Some people lived in the town, maybe they specialized in crafts, other people were out in the farms. So the individual might not have known all of the technology of the age. However, you could get the people who did know it, and they knew what there was to know about that technology. In the industrial age, things started to diverge because the machinery of the industrial age became increasingly complex. So people had to specialize in their knowledge. They had to specialize in energy gathering, in steam and gas engines, in transportation systems, in building, in communications. All the technology specialization meant that any given person only knew a little bit about all the technology of the age. You could collect experts, and the experts, for the most part, in that technology, have be on top of it. They could figure it out, but there was still things that experts didn't fully grasp because technology became increasingly interconnected. Now in the information age, we're really declining. Most people know very little about how our technology works. People don't know where water and food comes from. They don't know what cookies are and how they get on your browser and what they do. They don't know how the cell phone works. The individuals relative to the technology of our age cannot master it. But even experts can lose control because the technology is just so complex. So every once in a while there's a blackout of the energy system, and you get the experts together, and it'll take them a few days, and they'll get it back online again. But then it takes them months to go back and recreate, well, what happened? Look at all the logs and try to figure out what's going on. So in the information age, the technology is outgrowing our ability as humans, as individuals and as experts, to comprehend it. So what happens in the AI age? It looks like this curve is going downward. So when we're talking about intelligent agents, we're talking about artificial intelligence, which is hard. So can you really expect individuals to know that? And even the experts today, the AI experts, are concerned, well, how are we going to keep control over the technology? Forget any malevolent intentions. Just the technology that's trying to behave itself can be hard to understand exactly what the complications are. Well, we as engineers bear some responsibility here, and I think we can do something about the situation. The curve may be headed downward, but it's within our power to control whether it goes all the way to the floor or whether our society, as individuals and collectively, we maintain better mastery over the technology. We get along with technology better when we understand it. So what can we do to understand it? We're the technologists. We're the ones who can learn how AI works, do it for ourselves, communicate it to our friends, our associates, our neighbors, and help to make good policy decisions about where AI should be headed. So in other words, we need to become robot psychologists, and it's our obligation as engineers. So how do we do that? What does that involve? Well, for one thing, it involves sharpening and amplifying our theory of mind, how minds work. So theory of mind is actually a term that comes from cognitive science, and it refers to child development. And this cartoon illustrates it. So the dad is on the phone to the 3-year-old. He says, "What are you doing, Denzel?" And the kid says, "Playing with this." Now what this illustrates is that a 3-year-old is still developing theory of mind. So a 3-year-old has learned a lot. They learn how to walk, how to talk, how to ask their parents for a cookie, and even to master technology. They can talk on the phone to dad, and dad is far away. It's no mystery to them. Okay, dad's not here. I can still talk to him. But to a 3-year-old, when he says, "I'm playing with this," and he waves around his choo-choo train, it's obvious to him what he's referring to because he's holding it. He's looking at it. He doesn't appreciate the dad has a different sensory system and different knowledge. Developing that, appreciating that different minds, different people have different knowledge, different appreciation of the world, is what theory of mind is. And in children, this problem gets solved around age 4 or 5. And then there are other stages of appreciating theory of mind. Because you start to learn, as you grow older, that, well, people can hold beliefs, but sometimes they're false beliefs. People that can therefore be deceived, so they learn about telling the truth and lying. People can be uncertain about their beliefs. So how do you deal with uncertainty? You have to learn that other people have different goals and strategies, and if you learn what those are, then you can negotiate with them better. So people develop a theory of mind, and it's up to us to give ourselves the ability to develop, enhance our theory of mind about how robots work, AI systems, and that will benefit us because it will enhance our own theories of mind about ourselves. So let's just look at the basics of robot psychology. In order for a robot to even have a psychology, it's got to have some fundamental capabilities. Robot psychology, and any psychology, applies to people and robots, is built on a foundation called cognitive architecture. Cognitive architecture is a term used in cognitive science and in artificial intelligence, and it's actually not appreciated as well in artificial intelligence these days as it probably should be, although more people are starting to pay attention to it. It's a complex topic. I actually have a whole talk on cognitive architecture myself, but let's suffice it to say that cognitive architecture pertains to the fundamental competencies of an intelligent system. So that's its ability to have perception, to see and take input from the world, to act on the world through the motor system, to use language, to have memory. So that might include memory, short-term memory of what's going on in the here and now, or episodic memory, memory of specific events, shipping from memory to general knowledge, accessing the knowledge you have. Knowledge can be about skills, about facts, about general knowledge about the world where you don't know where it came from, and to do reasoning, to make inferences and deductions from what you see and what you know. That fundamental capability is something that we all take for granted. On top of that is psychology. So psychology, it pertains to the operational parameters. So once you have a fundamentally capable agent, well, what is it like actually? So that's about its motivations, its beliefs, knowledge, belief systems, its personality, if it has mannerisms and quirks, and if it has feelings and emotions, which we do, we don't know if AI will or will not, then that's at the psychology level, and our habits and our attention. So we take cognitive architecture for granted because everybody has it. Now, of course, some people have better memories than others. We recognize that. But mostly we orient to one another in terms of our psychology. But you only can have a reasonable, rich psychology if you have a good foundation of cognitive architecture. AI systems these days have only a very impoverished, weak cognitive architecture. And therefore, when they project psychology, they show behaviors, that's actually kind of faked. It's at a superficial or veneer level of the design of the agent, but it doesn't mean that it's got the full functionality and richness of a human psychology. One way of appreciating that is to recognize a fundamental distinction in different kinds of cognitive architecture. So theorists and philosophers of mind recognize 3 levels of reasoning sophistication of a cognitive architecture. I'm only going to talk about 2, the reactive and deliberative cognitive architectures. So we can think of a reactive level as being pretty much a stimulus response type of system, using think of it as if-then rules. If you're in a situation, you behave in a certain way. So they're good at running procedures. So you can start at some place, work through a procedure, and there are branch points. So you don't do the same thing every time. What you do depends upon the situation, but it's all mapped out in advance. They're predetermined storylines. And in fact, when you interact with a chatbot these days, that's what you're getting. And almost all of AI these days is doing something like a reactive type of behavior. In contrast, a deliberative behavior is, well, imagine you take all the little behaviors that you might line up in a procedure in a reactive architecture, that you break them into pieces, and you allow them to be reconfigured in any combination you want. So it can be dynamic in the situation, what happens. So in a deliberative architecture, you could have modular, reconfigurable chunks of behavior, and that supports a lot more interesting kind of intelligence. Supports reasoning by analogy, supports causal models. If I do this, what will happen? Planning, so planning several steps ahead. Imagining the world differently from what you have now. Imagining the past or the future. And putting together creative storylines. So this is what people can do, and there are a few AI systems that attempt to make deliberative architectures. They're interesting, but they're not that advanced yet. So that's where the field is going to be going. But given our deliberative architectures, well, what do we do with it? Well, one of the things we do is we understand the world. We make mental models. Now, of course, what we carry in our minds, what we think, we can only get through our perceptions, seeing and hearing and the other senses. So you can think of that as like a window on the world, but it's limited. It doesn't know everything going on in the world. We only get what our senses show us. So if we encounter another person, maybe they'll tell a joke, maybe they tell us they want something, they've got some interesting knowledge to share, we can only get a projection from our senses to what we see and hear. But having developed our knowledge of the world, our theory of mind, we form an inference about what this other person is thinking, what their beliefs are, what their intentions are. But what if this other thing we're looking at is not a real person, but an artificial agent? Maybe done with a reactive architecture. So it doesn't have deep cognition or understanding. We still see a very similar projection, especially if we only encounter it for a short period of time. And therefore, we're inclined to make an inference to give this thing more credit than it really has. We'll see maybe intentions and beliefs inside of it that it doesn't really have because it's actually running on a much simpler cognitive architecture. Its psychology is just painted on. An illustration of that is from the recent popular culture. We know that if we see a stone statue of a person, then it might evoke feelings in us, but we understand it's not a real thing, it's a real mind inside of it. It's just a stone statue, it's not going to behave. But what if what we're seeing is a mannequin that's got motors and a speaker, and it moves its mouth and talks and says things that sound sensible to us? Then we might be inclined to think that is actually an intelligent, sentient being. And this is a Sophia robot. It appears in news and entertainment shows from time to time. And when you see journalists write about this, they give it a lot of credit. They write things like this. Sophia has a certain set of preferences when it comes to working. She has interests in the business sector. So when we hear that, we think, oh, if a person has interests, then they're thinking about something. They've got a mind going on inside. In fact, the Sophia robot is a reactive system. It has no intelligence in it. It's just basically got pre-programmed responses that are, or a person behind the curtain typing at it. Yet, people want to give this a lot of credit. So part of our understanding theory of mind is understanding the difference between what we infer through what's projected on our senses and what's really behind the scenes. Now, it turns out that people sometimes like to give a lot of credit to artificial intelligence systems, and even ones that aren't that intelligent. And that was shown in 1966 by the ELIZA program. This is a conversational agent. It works only by typing, so it was one of the world's first chatbots. And it was designed to play the role of a Rogerian psychoanalyst. Now, it turns out that this kind of psychoanalysis works by asking questions of the patient, taking their answers, and then reflecting the answers back to them so they will think about them and cause them to reflect on their own feelings and statements. So this was written with some fairly simple natural language processing, and it was designed to ask questions, and then when it heard something or something was typed at it by the user, it would look for keywords and then reflect those back. So here's how the conversation goes. Is something troubling you? Men are all alike. What is the connection, do you suppose? They're always bugging us about something or other. Can you think of a specific example? Well, my boyfriend made me come here. See the keyword, boyfriend made me come here. Is it important to you that your boyfriend made you come here? He says, I'm depressed much of the time. I'm sorry to hear that you're depressed. It's true, I am unhappy. Can you explain what made you unhappy? So when the creator, Joseph Weizenbaum, put this program out for use by people in the AI lab at MIT and his secretary and people from his family and community, many of them started taking this thing very seriously. And they said, oh, this is really helping me. It's understanding me. Wow, what have you created? It's wonderful. I don't want you to look at what I'm typing because it's private. So they gave it credit for doing a lot more than what it was. It's a simple reactive architecture, not doing anything smart at all, not understanding the user at all, but they wanted to believe in it. Weizenbaum reported, extremely short exposures to a relatively simple computer program could induce a powerful delusional thinking in quite normal people. So that would be unfortunate if we made this mistake about our AI agents. We have to really understand what they're really about and not. Now, it's not the case that we always are deluded. I mean, we have jokes like this one about dogs. We say, okay, Ginger, I've had it. You stay out of the garbage. Understand, Ginger? Stay out of the garbage or else. And we understand. We make a joke about it. Ginger only hears Ginger, blah, 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 Ginger. So we understand that things that have complex behaviors, they look like they have a mind of their own, might be limited, more limited than that. So we have to build on this intuition about what another mind is like when we contemplate the minds of artificial intelligence agents. So this is part of our training to be a robot psychologist. All right, so now let's get down to some serious work about robot psychology. How do conversational agents work? So these are the things we're talking about. We have Alexa running on Echo, Google Home, and this is the Jibo robot. So Jibo is one of the first social robots for the home. This thing actually has these swivel joints, so we can look around and dance. And it's designed, the artificial psychology that was designed into it is just different from these utilitarian agents over here. Jibo was designed to be a character. It was made by people who had been trained at Disney, and it had this curious little sense of humor. It would tell little wisecracks and jokes, self-deprecating. It made little pictures on its screen there. So it was a different kind of experience psychologically as a human than a utilitarian agent. And it was really fun to have around. Unfortunately, the company went out of business, so they're not doing it anymore, but it was a first foray into that space. So we'll consider what's really smart about these things, which is question answering. So I can ask Alexa, who won the 1934 World Series? And it comes back and it says, the St. Louis Cardinals beat the Detroit Tigers 4-3 in the 1934 World Series. Well, that's pretty impressive. I mean, if you wanted to look that up, you'd have to go to the library, you'd have to find a book on baseball, and it would take probably half an hour at least to learn that. So how does a conversational agent, how does it be that smart? Well, to understand that, you have to appreciate the ingredients of intelligence. So there are 3 pillars of intelligence: knowledge, pattern matching, and reasoning. So knowledge is information in some structured form so you can compute on it. You can look things up, find answers. Pattern matching is having some piece of information and finding something similar when it's not an exact match. And reasoning is having some piece of information and some rules of inference or deduction and deriving other pieces of information from it. So this is what it takes to make a fully intelligent system like ourselves and like we're trying to do with artificial intelligence. So let's take a little tour through knowledge. We're going to look at a particular form of knowledge called knowledge representation called a knowledge graph. And we'll put that together with a particular type of pattern matching in the natural language processing pipeline called entity intent recognition. And those are the key ingredients of a question and answer conversational agent. And when we do that, we're going to be able to do a little bit of robot psychology, a little bit of reverse engineering, and we'll find out where the weakness is when it comes to reasoning. That's where we're going. So let's start off with what is the architecture of a conversational agent. So it's a loop, actually a form of what's called the perception action loop. It takes some speech in, and speech recognition, automatic speech recognition, produces words. Words are sent to natural language processing that produces a structure called a logical form. So this is a computer representation of the meaning, some interpretation of the meaning of the words that's accessible to the computer. Then the Dialog Manager evaluates that, and it figures out what the response should be. And that's also in a logical form. Natural language generation turns that back into words, and then text-to-speech turns that back into what you hear. So in order to answer a question, you have to access knowledge, and that happens up here in the Dialog Manager. There are three major types of knowledge resources that come into play in these things. There's the knowledge graph, which we'll look at. They also can use structured databases that we're familiar with. And they also can look up on the open internet. So they have means of indexing Wikipedia and finding articles and passages that might be relevant to the question. I won't go into that in much detail, but we'll see an effect of that. So let's look at a knowledge graph. So knowledge is a store of information in some organized form. And here's an example knowledge graph that's part of a much larger graph. And this one knows about characters in TV series. So for example, it knows that Leonard Nimoy is an instance of a person. The person Leonard Nimoy played a role as Spock. Spock is a character in Star Trek. Star Trek is an instance of a TV series. So a graph is nodes and links. Now this particular knowledge graph example I've shown has two types of nodes or entities. One is called a type node, and that's a class of things. Like a person is a class of individuals. And the other type of node is known as a token node, and that's a particular individual. So Leonard Nimoy is a particular individual instance of the class of persons. Now in this particular knowledge graph, I've shown that there are two types of nodes, and the links are labeled with their relation types. But different knowledge graphs have different designs in this manner. So some of them may have only one type of node, not a distinction. Others might have a hierarchy of nodes. Maybe a TV series is a type of entertainment venue. The design parameters are called the ontology of the knowledge graph. Ontology means the nature of reality. And it's a word that comes from a branch of philosophy called epistemology. Epistemology is the philosophy of knowledge. So what does it mean to have knowledge about the world? How do we acquire knowledge? How do we verify knowledge? Do we trust it? How do we structure representations of knowledge? So if you're an engineer working in a company that makes knowledge graphs, you care a lot about what these philosophers have to say, because the design decisions you make about ontology have big consequences about what kind of knowledge you can represent about the world, how well that knowledge is going to work, whether you can look up things, whether you can verify your knowledge. Epistemology is very important here, and the ontology, there are many ontologies used for knowledge representations. There are a number of knowledge graphs that are actually in use today, quite a few, known as Freebase, Wikidata, based on the Wikipedia data, Yago, Google Knowledge Graph. So these are big. They have on the order of millions or tens of millions of entities, nodes. And the relations, if the relations are typed, then there could be thousands of link or relation types. And the facts, the actual arcs in the graph, can be in the hundreds of millions or even billions. So that's a lot of facts. Now notice, though, that they can't contain all facts. I mean, human language is bigger than a knowledge graph could possibly be, because we could say an unlimited number of possible things, statements of fact. So it's only a fraction of all the things people could possibly say, but it's still a lot of facts. So how do we use a knowledge graph to answer this question? Who played Spock in Star Trek? Well, we have to do some natural language processing. So there is a technology used in AI these days called natural language processing pipeline, and we can apply a few pipeline elements. One of them will be part of speech tagging. So for example, the word who is a pronoun, refers to a person, but the person is not know. We don't know what that person is. Played is a verb, in is a preposition. So we can find those words in this sentence, and we can also find named entities. Named entity recognition looks for things that are known in the world. So Spock is known to be the name of a character. Star Trek is known to be a TV series. Once we label our sentence in that way, we apply another pipeline element called entity intent extraction. And it's got two jobs: to find an intent and some parameters. So intent is, what's the purpose of the utterance on the person's part? Is it supposed to be a question? Is it a command? Like set a timer? Is it a statement of fact? So the intent part of the entity intent extraction looks for question words, command words, and other words that are indicative of what the purpose is. And then it looks for the parameters in entity names and relation words. And it looks for patterns for how these words go together. So one syntactic pattern would be you start with a question word, then you have a relation, an entity, a relation, and another entity. The patterns, they might be variants on the pattern. They map to a logical form. So logical form is a computer-readable expression. In this case, I've drawn it with parentheses and commas, like is common in some computer expressions. And this is a template. This template says there's a question about a relation with two entity arguments. So given the original sentence and this pattern match, we can fill in the blanks of this template and arrive at our logical form, which says this question, who played Spock in Star Trek, maps to a logical form, which is a question about playing a role, and there's a person, and what we're looking for is who is the person? That's the question. And then what else pertains to the role is the character. And the character is known to be Spock, and we know that Spock is a character in a TV series known as Star Trek. So we can use this to access the knowledge base. Now it turns out a logical form written like that can be rewritten. You could study that and see, hey, we could turn that into a graph also. So these are equivalent. They're just written out differently. But this is our question, and you can see the thing we want to know the answer to is this question mark here of what is this person that has these properties. So once we have our query in the form of a graph, we can apply an algorithm called subgraph matching. Very common algorithm in computer science. So this is a part of our much bigger knowledge graph. Subgraph matching means we try to find an alignment between the nodes and links in this graph onto our bigger knowledge graph. So when we can find a part of the knowledge graph where we can say, oh yeah, these are matching, then we can say we fit our subgraph into the larger graph. Now the question mark is a wild card. It'll fit anything. But once we've done the subgraph matching, we can go to our larger knowledge graph and we can say, oh, well that node was Leonard Nimoy. So now we can fill in the blank. That's the answer to the question. So that's in principle how we can use natural language processing and a knowledge graph to answer questions. So let's try it out. So we can ask Alexa, who played Spock in Star Trek? And it gives a direct answer. Spock was played by Leonard Nimoy in Star Trek, the original series. So in this case, it didn't just say Leonard Nimoy. It actually had a little piece of text attached to it. Probably people ask this question a lot. We can ask other questions, all related to the same query graph, by manipulating the query graph. who did Leonard Nimoy play in Star Trek? Gives a correct answer. Is Leonard Nimoy a person? So this is a different kind of question. It's asking a yes or no question about a link. And it says, yes, Leonard Nimoy is a person. In fact, he says he has a little blurb about that. He's an American actor. Let's ask some other questions. As a reminder, this is part of our query graph. We can ask, is Star Trek a television series? So we can read off. It's looking at that instance of link. Is Spock a character in Star Trek? Yes, Spock is a fictional character. If I ask, is Spock a character in a television series? It doesn't give me a direct answer. The way these things work is they have a number of knowledge sources. They parse the query according to what each of these sources are good at. So it makes a knowledge graph query, like we've seen, but it also says, can I find the answer to this on the internet database? So it does some text indexing to try to find a plausible answer. And it comes back with all the plausible answers from all the knowledge sources, and each one has a probability score or a confidence, and it chooses the one that it's most confident in. So evidently, this question, is Spock a character in a television series? Here's the knowledge graph for that. It said, is it a character in a television series? But I haven't said what the series is, so I put it kind of a blank there. Apparently, this knowledge graph, or this query graph, it didn't find an adequate fit for. So it did a back-off strategy. It says, okay, I'm going to use the web result, the Wikipedia article, and it's going to read me off something about that. We can ask other kind of questions. And by reverse engineering these things, it can be fun. You can learn a lot. So is Star Trek a pineapple? I bet it's never been asked that. But it gave me a very direct answer, no, which tells me that it's actually looking at the knowledge graph. And by saying, well, look, I know what kind of thing Star Trek is, and it's a TV series. It's not a pineapple. Is Star Trek a pineapple in Mexico? Well, logically, no, it's not a pineapple. It's not a pineapple in Mexico. But Alexa was confused. It says, I'm not sure. So something about that query graph was not a good enough match for it to give me a direct answer. You can ask other questions. Is Los Angeles a city? Yes, it gives a good answer. Is Los Angeles a person? And it gives me this wacko answer. The Rams are the third in the NFC West. So sometimes these things are kind of dumb. Now let's push it in a slightly different direction. Is a refrigerator heavier than a peanut? It says yes, a refrigerator is heavier than a peanut. Very good. Now, do you think that was stored in the knowledge graph? I think it's unlikely that that was entered. It's not a question that probably gets asked. And if it were, then the knowledge graph would have to be pretty huge, because you think of all the things questions of that form it could ask. I think there's a million entities, and there's only like 10 relations that you might even want to probe, like bigger than, lighter, taller, shorter. A million times 10, that's 10 trillion facts of this nature. That it seems unreasonable. The knowledge graph is not that big. And it doesn't make sense to put that kind of question in the knowledge graph. So what's probably happening here, what makes sense is to do a little bit of reasoning. So what do? You say, well, we're going to make a multi-step process. We'll look up what's the weight of a refrigerator, what's the weight of a peanut, and compare them. And that's a way of computing this answer. So we can test that by doing a little more robot psychology, a little reverse engineering, which we as engineers love to do. Is Barack Obama taller than William Shatner? And this time it doesn't give a yes or no answer, but it does give a direct answer. Barack Obama is 6'1", which is 3.48 inches taller than William Shatner. William Shatner is 5'9" inches tall. So it tells me that it's probably using some sort of comparison there. It could have computed yes, but it didn't. Although there's something kind of wacky here. What's the difference in height between 6'1" and 5'9"? It's 4 inches, not 3.48 inches. So what's going on there? Now I tried to figure this out. I said, well, maybe it's using the metric and then rounding, but I could not make the numbers work. But if you can figure it out, let me know what you think might be happening there. That's kind of bizarre to me. All right. What about other height comparisons? Is Barack Obama taller than a toaster oven? Sorry, I don't know that one. Well, why would that be? Maybe it doesn't know how tall a toaster oven is. You can ask the question, how tall is a toaster oven? And it said, oh, a Black & Decker toaster oven is 9.4 inches tall. Maybe it can only compare a person's height to a Black & Decker toaster oven. So you can ask that question. Is Barack Obama taller than a Black & Decker toaster oven? And it says, I don't know. However, if you say, is Barack Obama taller than a washing machine? It says, yes, Barack Obama is taller than a washing machine. So what's the difference between a washing machine and a toaster oven? Well, if you ask how tall is a washing machine, it says the average washing machine's height is 36 inches. So, and if you play with this a little bit more, you find out if it's a device or an object that it knows the average height of, it's able to do this comparison. But if it's a specific instance like Black & Decker, it doesn't. So it could really be really fun to play this game. You could play other games. Will a baseball float in beer? Can you tune a violin with a piano? Can you tune a violin with a refrigerator? Now, all of these, Alexa is totally perplexed, has no idea. You can't blame it. I mean, this is the sort of a question that when you ask a person, what do? You kind of imagine in your mind, oh, baseball. I've seen the baseball floating in San Francisco Bay when a home run is hit. What's the specific gravity of beer compared to salt water? I've probably, if you play the piano, you can picture a person, you've probably seen a person tuning a piano with a violin with a piano. What about a refrigerator? Then you're going to think, okay, what's the sound of a refrigerator? Probably 60 hertz. Is there a string on a violin that's a multiple of 60 hertz? So we engage in steps of reasoning, naturally. This is not something that one of these agents can do. It requires really common sense knowledge, and common sense reasoning. And that turns out to be the big, big deal in artificial intelligence. The holy grail of artificial intelligence is common sense knowledge, common sense reasoning that the 3-year-old has. That is what we have not achieved in artificial intelligence. The cognitive architecture does not yet support that. So we are dealing with agents that have much simpler reasoning systems, but they're ones that, fortunately, we can actually get some insight into by asking questions. Now let's focus on a slightly different aspect of the conversation with one of these agents. If I ask, Alexa, who won the 1934 World Series? It tells me the St. Louis Cardinals beat the Detroit Tigers 4-3 in the 1934 World Series. Well, that's smart. Here's a follow-up question. Alexa, who was the president then? This might answer your question. The president of the United States is Donald Trump. Well, that's not too smart. That's very unfortunate. And I even asked it, I said, use the word then, referring to 1934, and it even said 1934. So what's wrong here? Why can't it know that the context is the president in 1934? Well, this illustrates another weakness of these conversational agents in the Dialog Manager. When a person engages in a back and forth dialogue, we build up a set of concepts in our minds, in our short-term memory and intermediate-term memory, ideas that come to mind, like a team, a date. World Series might bring to mind associations like baseball and professional sports. And these ideas, this context, is a resource we use to interpret what we're hearing. And it's something that we build on, we contribute to by reference when we respond. But so when we hear the word then, we think, well, okay, was there some time in recent, some time that was referred to, and we can key on a recent date. This kind of context awareness, it turns out to be very, very hard to do because it pulls together all 3 pillars of intelligence: knowledge, pattern matching, and reasoning. And it's something that today's conversational agents really cannot do very well. We can still do some experiments, reverse engineering, and we can look for conversational accountability. So here's a sequence that tells us something about what might be going right or wrong in context maintenance. I ask, when were Barack and Michelle Obama married? This is asking Google Home. Google Home says, Barack Obama has been married to Michelle Obama since October 3rd, 1992. What is his birthday? August 4th, 1961. So here it got the pronoun reference. And mostly these things can interpret a pronoun with respect to the previous sentence. So in this case, it got that right. If I ask, what is her birthday? It tells me still August 4th, 1961. Now wait a minute. Her refers to Michelle, and that was just 2 turns ago. If I ask it up here, what is her birthday? It knows Michelle Obama's birthday. That's not the problem. So apparently the context awareness of Google Home only goes back 1 turn. It doesn't go back to the previous turn. Now it's possible it misheard me. Maybe it heard his instead of her. So this is where we would like to have some accountability on the part of these conversational agents. I want to be able to ask it, what was my question? Did you hear me correctly? If I ask, what was my last question? It says, Google Home says, I heard, what is her birthday? I was impressed by this, because that's a measure of accountability. It was able to tell me back what it heard. So I know now that the speech recognition was not the problem. It got her correctly. And by extension, the entity intent recognition probably understood it was looking for a female person's birthday. So the problem apparently lies in the context manager. The dialog manager is lacking context to look far enough back at the context. If I ask for a little more accountability to follow up on that hypothesis, I ask, why did you tell me his birthday? It says, I don't know why. So it only goes so far. I think we can help here. Because if we do this kind of experiment ourselves, we should be asking these things for accountability. We should say, why did you tell me that? Did you understand my question? Now, can you pressure these companies into giving accountability? Possibly, because they're very sensitive to the public reaction. They're very sensitive, when they go to Congress and testify. And if users are asking for it, they're demanding accountability from the AI, they'll probably want to supply that. And their own engineers want to do that. So I think they need a little nudge from us, the people who are going to reverse engineer these things, and try to explain to our neighbors how these things work. Let's look at one more step in a dialogue management story. So the dialogue manager is where it decides how to interpret what was said in terms of what an appropriate response is. Natural language processing uses entity intent extraction. That's the primary means these days. And if you want to build a conversational agent, there's a lot of tools out there for you to do it. And these are some of the entity intent extractors, the NLP toolkits that you can use. Amazon, Google, IBM, Microsoft, the independent one called Rasa. They'll all do about the same thing, deliver you a logical form. The hard part is in the dialog manager. These days, there are about 3 strategies used for dialog managers. One is just custom logic, just a reactive system, just like I drew on that previous slide. If the conversation is here, this is how I respond. And there are actually tools for designing conversation flows and trying to corral them. So if people tend to go off the rails, they ask irrelevant questions, then the response will try to get them back on track to what the agent knows how to do. So if you're dealing with a chatbot, you're probably dealing with a custom rule logic dialog manager. There are some attempts to make machine learning systems to decide how to respond. Those are still in the research stages, and I don't think they've made it that far into the open world. The primary and the most sophisticated type of dialog manager that you're liable to encounter these days is called slot filling. And it's simple logic. It's not very fixed logic. It's a little bit dynamic. And the idea is you have some data structure that you need to fill in the slots for, some values that you want values for. You might be communicating to the agent, or you might be receiving it from the agent. But the dialogue is designed to accomplish this back and forth for a fixed set of objects. So if you're booking a woman's haircut, then you need to know, who's the person, what's the date, and what's the time. So let's do an example of that. I'm going to play you a clip from an announcement that Google made in May of 2018 that made a huge splash, the Google Duplex Google Assistant. And I want you to remember here that the second person speaking is not a person, it's the Google Assistant. And follow the logic of the conversation. It's essentially slot filling. And I'm going to follow along, and we'll listen to the slot filling happen as a haircut is booked.
How can I help you? Hi, I'm calling to book a woman's haircut for a client. I'm looking for something on May 3rd. Sure, give me 1 second. Sure, what time are you looking for around? At 12 p.m. We do not have a 12 p.m. available. The closest we have to that is a 1:15. Do you have anything between 10 a.m. and 12 p.m.? Depending on what service she would like. What service is she looking for? Just a woman's haircut for now. Okay, we have at 10 o'clock. 10 a.m. is fine. Okay, what's her first name? The first name is Lisa. Okay, perfect. So I will see Lisa at 10 o'clock on May 3rd. Okay, great. Thanks. Great. Have a great day. Bye.
All right, so what was so impressive about that were two things. First of all, how natural it sounded. So the manufactured psychology, the personality of this thing, seemed very real to people, and it creeps some people out, frankly. That's why Google's being very careful about this. And that was done by machine learning. So they had a lot of real people call into hair salons, book appointments, and they took that data to train some deep learning systems that would emulate the speech patterns of real people talking. The second thing that's pretty impressive is the Dialog Manager itself, its ability to do the slot filling. Because there was a part there where it wasn't a direct answer. There had to be a little negotiation about the time. Because 12 o'clock was not available, but okay, what does she want? Oh, if it's a haircut, then you can do 10 o'clock. So I think that's a pretty impressive degree of slot filling, enhanced slot filling behavior that they managed to put into the system. The logic itself, they don't publish papers on this, so they haven't published what the logic is, but I think we can pretty well, based on what we know, read in that that's probably the strategy they were taking. So that's kind of the state of the art of, and probably the hair salon person did not realize it was talking to an assistant. This is an ethical question that Google has addressed, and I understand they're now calling stores in New Zealand to find out, if they're closed during the holiday. But I think the policy is moving toward, and this is part of its brand image, being transparent, saying I'm an agent calling on behalf of. But this is something to be tested because we want to have transparency out of these things. We don't want to be fooled. I think that's an important part of having us all build our theory of mind about whether we can trust these things to be what they say they are. A final example to look at is social chatbots. So this is another piece of the conversational agent story. Turned out that when Amazon released the Echo with Alexa on it into people's houses, they set timers, they played music, they asked questions, but some people also wanted to talk to it. Maybe they were just experimenting, but maybe they were lonely, they wanted to have a conversation. So Amazon said, well, look, this is too hard, it's not an engineering problem, it's a research problem. So they created a program where they had university teams try to do research and build systems that would chat with people, just social chat. So this is not directed to any particular task. They put $1 million up and about 20 teams per year compete for this. And their goal is to just engage a person speaking for as long as possible. And I think their benchmark or their goal is to hit 20 minutes. And also, if you can rate the system, how much do you want to talk to it? So if you have an Echo in your own house, you can say, Alexa, let's chat, and you can play with this thing. It'll say, let me get you a social robot, and it'll come on and try talking to you. Every year, the winner or the winning teams publish the papers about what they've done. This is the winning team from 2018. It's called Gun Rock. This is their architecture, and it's got a lot of familiar things. It's got some natural language processing, some segmentation, named entity recognition. It has some access to a knowledge base, to various knowledge bases. It's got a dialog manager that looks for keywords, for intents, the topic that a person is talking about. And then it has a dialogue strategy. The strategy is basically ELIZA. It asks questions, and it listens for keywords coming back from the user. And it tries to find something in a knowledge base or on the internet that's relevant to that topic and put it back to the user, sometimes making a statement, sometimes in the form of a question. And the users might be fooled. If you're credulous, you'll say, oh, okay, this thing's really talking to me, and you'll let it follow along wherever the conversation goes, and you'll be engaged. So it's like a Paro robot. You can keep people company. But bear in mind that its strategy has no intelligence inside of it whatsoever. It's just basically doing an ELIZA program. So it's a little bit more like the Sophia robot that portrays itself as having a conversation with you when it's really doing tricks, you'd have to say in fairness. But again, this is fun to play with, and knowing what we know now, and you know now about how to reverse engineer these things, you can design systematic ways of talking to these chatbots and learn about them. Learn what topics they're able to work with and what not. Learn what their ability is at keeping context in a dialogue. Learning when it gives up and turns around and parries a question back to you because it's gotten lost and it's trying to keep you entertained. So that brings me to the conclusion. Modern robot psychology, three takeaway points. First of all, we are moving to an age of autonomous AI technology, and we can all take responsibility as engineers for understanding how these systems work as well as possible by taking an interest in them and by playing with them, by becoming robot psychologists. And it turns out robot psychology is fun. And it's not as mysterious as it seems. Once you have a little bit of understanding of what's going on inside, then you know what questions to ask and how to interpret the answers. So let's all go out and be robot psychologists. This is me. Appreciate your comments and feedback. This is my website, email, or let's take some discussion now.